Welcome back to the full fly-by-wire electric outboard project. In the 11th video 2 weeks ago, we built an EMC-compliant power supply for our electronics. Card here, link in the description. In this video, I want to implement a temperature monitoring. Remember, all this goes in the end into a watertight, airtight case and, well, things might heat up. Enjoy! There are 3 common options to do digital temperature measurements. First, we could use an integrated digital sensor. For example, an DS80B20 or an DS18S20. I made a couple of videos about those. Links in the description. Second, we could use a thermocouple in conjunction with an amplifier, and that would be a very special amplifier, not simply an op-amp, and then digitize the output of that amplifier with an ADC. Fortunately, the amplifier part and the ADC part you find integrated in some chips, like, for example, the MAX6675 or the MAX31855. I also made a couple of videos about those. Links in the description. Third, we could use a thermistor, that is a resistor that changes its resistance with the temperature in conjunction with an analog to digital converter. A DS18B20 will set you back less than a couple of bucks, while a combo of a thermocouple plus a MAX6675 will set you back a few bucks. A thermistor you can get for a few dozen cents. We still have an unused input on our analog to digital converter. And we don't need the huge temperature range of thermocouples, hundreds of degrees Celsius. And we don't need the precision of a digital sensor. So, a thermistor it is. There are 2 basic types of thermistors. Negative temperature coefficient NTC thermistors and positive temperature coefficient PTC thermistors. The resistance of an NTC thermistor decreases as the temperature increases. And that happens in an exponential way, not in a linear way. The resistance of a PTC thermistor increases as the temperature increases in an, almost linear way. Though that's not true for all PTCs. There are PTCs that have a quite funny curve, that is, the resistance first decreases a little bit with the temperature and then at a certain point it increases dramatically. Such PTCs are usually used in polyfuses or resettable fuses. When they get too hot, they increase their resistance enormously and they'll shut off your circuit and hopefully save it. Those PTCs with an almost linear temperature resistance curve are always silicon-based thermistors. To calculate the resistance of an NTC at a temperature Tx, you use that formula. You have the resistance at a temperature T0 and you multiply that by E to the power of B, that's a constant, and then in brackets 1 over the temperature you're measuring, Tx, minus 1 over the temperature T0 at which you measured the resistance T0. In the datasheet, you have normally given all these 3 values, R, T0, T0, and the B. The resistance of a silicon-based PTC at a certain temperature Tx is calculated using that formula. Again, you have the resistance at a temperature T0 and you multiply that with 1 plus a temperature coefficient, and then in brackets the temperature you are measuring minus again the T0 at which the initial resistance was measured. In the datasheets you usually find these two constants here. So the resistance at a certain temperature, that's often R25, so the resistance at 25 degrees Celsius, and then your temperature coefficient. That's also sometimes called temperature coefficient resistance and is often given for different temperatures. Remember, this is only approximately linear. It's also a slight curve. Considering we are currently using an 8-bit MCU with 20 MHz, an Arduino Nano, that formula brings a whole lot of computational costs with it. I mean, we have here 2 multiplications, 2 divisions, and we have to calculate an exponential function. While here for the PTCs we have only 2 multiplications. That's much better. So let's use a PTC. We will be using a Texas Instruments TMP61-Q1, automotive grade or whatever, plus minus 1%, 10 kilo ohms, linear thermistor, so silicon based, and of course it's a PTC. As already stated in the headline, it has a nominal resistance of 10 kilo ohms at 25 degrees C. They call that the R25. And that value is given with a tolerance of 1%. It has a temperature coefficient, or they are using here the term temperature coefficient resistance, of 6,400 parts per million per degree C at the 25 degrees C point. And that's given with an accuracy of 0.2%. Please note, 6,400 parts per million is 0.64%. So yeah, that thing is relatively sensitive to temperature changes. Please note that this thing is polarized. It has a positive pin and a negative pin. I'm not sure if that applies to all silicon-based PTCs, but that one here we're using is polarized. And it clearly states thermistor minus and plus terminals for proper operation ensure a positive bias where the plus terminal is at a higher voltage potential than the minus terminal. There are 2 important absolute maximum ratings for us. First, the voltage across the device should not exceed 6 volts. And the current through the device should not exceed 450 microamps. The recommended operating conditions are even more restrictive. So voltage across the device should be between 0 and 5.5 volts. And the current passing through it in the temperature range we are interested in, so between minus 40 degrees C and 150 degrees C, between 0 and 400 microamps. Looking at the further electrical characteristics, we already talked about the resistance and the resistance tolerance, as well as the TCR25 temperature coefficient of resistance and the tolerance for that. Please note that because the curve is not completely linear, they also give you a TCR for minus 35 degrees C and a TCR for 85 degrees C and the related tolerances for those. Now that we know which thermistor we are using, let's talk about the circuit. And it will be very similar to the water intrusion detection circuit we developed in video number 10. Card here, link in the description. A long-time viewer of my videos pointed out in the comments that my solution for the problem that charging up the sampling capacitor within the ADC while that huge resistor here takes far too long by introducing a buffer capacitor at the input is far from perfect. And he was absolutely right about that. You see, recharging that capacitor after we partially, 1/5000th of its charge, approximately, discharged it through the sampling capacitor also takes some time. The tau time constant of that RC element here is about 560 kiloohms times 100 nanofarads, so 56 milliseconds. So we can expect that capacitor to be fully discharged after 5 tau, so 580 milliseconds. But we take currently a sample, partially discharging it again every 100 milliseconds. So we just reduced the error from something really bad to something acceptable, at least for that application. Remember, we just wanted to know the order of magnitude of the resistance of our sensor. If we wanted real precision in this scenario, we would have to insert an amplifier here to get down our signal impedance to the 1 kiloohm that is recommended by the ADC's manufacturer. Anyway, here is the circuit for our temperature monitoring. Again, we have a voltage divider between our 2.5 volt Vref and ground. And again, the upper resistor in the voltage divider is of the fixed type. I choose here 10 kiloohms with 1% tolerance, and our lower resistor is again our sensor, in this case our PTC, which has incidentally 10 kiloohms nominal at 25 degrees C, also with a tolerance of 1%. There is no law that states that both of these resistors should have the same value. It's just a rule of thumb for a good starting point. Since both resistors do have the same value at 25 degrees C, at least nominal, we should be here at our tap-off point at 1.25 volts, so exactly half of our reference voltage. And to get the time constant stuff out of the way, the tau of that RC element here, I called it tau 2, would be 10 kiloohms times 20 picofarads, so 200 nanoseconds. So we need a 5 tau 2 or 1 microsecond to fully charge our sampling capacitor. And remember, the sampling time, that is the time that switch is closed in our ADC, is 1.5 cycles at 2 megahertz, so only 0.75 microseconds. So I choose again to use a buffer capacitor, which is 5,000 times larger than the sampling capacitor, reducing the error below 1 lsb. But this time the tau of our upper resistor here and our buffer capacitor, I called that tau 1, is only 10 kiloohms times 100 nanofarads, so 1 milliseconds. So we only need 5 tau 1, so 5 milliseconds to fully recharge that thing. And I don't plan to take a sample more often than every 100 milliseconds. So this works out fine this time. But what sensitivity can we expect from that circuit? let's assume we increase the temperature by 1 degree C above 25 degrees C. And I hope you remember your formula. We take the 10k ohm nominal and multiply that by 1 plus the 6400 ppm per degree C. That gives us a resistor value of 10.064K for, well, 26 degrees C. If we do our voltage divider math with that new value here, we get 10.064K divided by 10K plus 10.064K, and that's 1.2540 volts. So a delta of 0.0040 volts. And with our 12-bit ADC, that's approximately 6.5 LSBs. So yeah, we will notice if the temperature shifts by 1 degree. However, our nominal value of 10K at 25 degrees C is given with an accuracy of 1%. So it can already be anything between 10.1K and 9.9K. So really having degrees Celsius precision, no, not right out of the box. One last remark. You want to keep the power you burn inside your PTC as low as possible because it's heating up the PTC, and this becomes another error source. In our case, we have here 125 microamps flowing, so 2.5 volts divided by 20K, and we're dropping across the PTC at 25 degrees C, 1.25 volts. So we're burning inside here 156 microwatts. I think that's acceptable for our application. And here's how the whole thing looks on the breadboard. The green wire is jumpering over the 2.5 volt reference voltage from our current sensor. And that goes here into a 10K 1% resistor, which is connected to the positive end of our little PTC. The negative end of our PTC is going down to ground, so that's our voltage divider. The center point of our voltage divider is buffered to ground via that 100 nanofarad capacitor, and then the yellow wire is jumpering the center point over to the input 2 of our ADC. Now, before we go any further, let's measure the real resistances of our part. So the little resistor comes in at 9.96 kiloohms. And our PTC comes in at 9.97 kiloohms. And that at a temperature of 27 degrees C according to thermocouples. However, I'll trust my lab thermometer a little bit more, and it says, let's zoom in, 27 degrees. Yeah, so let's say 27 degrees. Before we move on to our code, a bit of PTC thermistor, respectively voltage divider math. I've already shown you that formula here for calculating the resistance of a PTC thermistor at a certain temperature Tx. Thanks to the magic of math, we can write this in that form here. So our temperature Tx is equal to our resistance at the temperature Tx minus our resistance at the temperature T0 over our resistance at the temperature T0 times our temperature coefficient plus our temperature T0. Now, that might look a little bit funny at the first glance, but consider that. Our resistance at the temperature Tx minus our resistance at the temperature T0 is just our change in resistance. And our temperature coefficient, which has the unit 1 over degrees Celsius, multiplied with the resistance at the temperature T0, gives us a temperature coefficient in the unit ohms per degrees 0. So on the top we have ohms, and at the bottom we have ohms per degrees 0. The ohms, of course, go away, and we are left with 1 over degrees 0, which is degrees 0. But that's only the temperature change, so we have to add our temperature 0. Now for the voltage divider we are using with a V in and a V out and an R upper and an R lower. You know the usual voltage divider formula. So V out is equal to V in times R lower over R upper plus R lower. And we can write that as R lower is equal to V out times R upper over V in minus V out. This becomes a bit clearer if you consider that V in minus V out is just the voltage dropped across the R upper, and V out is of course the voltage dropped across the R lower. Our V in is of course the V ref of 2.5 volts we use, and our R at the temperature X is of course the R lower in our voltage divider, and the V out of our voltage divider is of course the voltage we feed into our analog to digital converter. And to calculate that voltage, we just take the binary ADC value and multiply that by our reference voltage over 2 to the power of our ADC resolution minus 1. And now for the code. Same old, same old. Sorry for that. Anyway, it has exactly the same structure like our other class files, only we have now here of course a class temperature with the usual deleted default constructor and our real constructor. Our begin method does nothing, and we come back to the get method in a second. After we had a look at some private constants. So first here we have a float vref, that's our 2.5 volts. Then we have an unsigned integer 16, our ADC max value, which is 2 to the power of 12 minus 1, so 4095. We have here an unsigned integer 16 for our R upper, which is 10 kilo ohms. We have here as an integer 8 our T0, which is 25 degrees C, unsigned integer 16 again, our resistance at that temperature, which is also 10 kilo ohms according to the data sheet, and our temperature coefficient, which is 0.0064. The unit here still 1 over degrees C. That's our 6400 ppm. Our get method returns a signed 8-bit integer, in degrees C of course. And we have here some variables, an unsigned integer 16, that will be our ADC value. We have a float, that's the V out of our voltage divider. We have another float, that's our resistance at the temperature Tx, and we have yet another float, that's our temperature Tx, which we are interested in. So first we get the ADC value from our ADC by reading the channel we passed in the constructor. Then we calculate our V out with the math I explained to you. So the ADC value times our Vref divided by the ADC max value. Next, we calculate our resistance at the temperature Tx, which is, of course, V out times the resistance of our upper resistor divided by Vref minus our output voltage from the voltage divider. And finally, we calculate our temperature Tx, which is the resistance at the temperature Tx minus the resistance at the temperature 0 divided by the resistance at the temperature T0 times our temperature coefficient plus T0. And at the end, I round that to whole degrees and I return it. That's it for temperature.h. In our sketch, I added another channel constant here for our ADC temperature channel, which is, of course, the channel single input 1. Further down, I create our temperature object with the monitor ADC object passed and the monitor ADC temperature channel. In the setup, I also call now temperature begin. And finally, in the loop, in the display block, I print out our temperature by calling a temperature get. And here are the results. As you can see, I'm reading our temperature here and I put the thermocouple. Can you see that? Probably not. It's very small, but I placed it very close to our sensor. So we have at least an idea how warm our sensor should be. Let's stop auto scroll for a moment and have a look at the numbers. And the first thing we noticed here is, of course, it's noisy. What else is new? But we have here values between 33 and 28. 33 and 28. So, 30.5 degrees is the center value. So we are, without any calibration, we are measuring here 27, so 3.5 degrees off. And we have about 5 degrees noise. Well, that's good enough for, detecting if we are cooking off our electronics inside the housing. But especially the noise could be a little bit better. And maybe we need some calibration. But temperature calibrating is always a pain in the behind. And don't forget, I also have some measured values for our resistor and our PTC thermistor. So maybe we can, at a later point, put them into play. But for now, I guess that's good enough. It's working. That's it for today. I guess next time we do some general housekeeping. To get rid of the noise here with the temperature measurement, we also should introduce oversampling. And I promised you I would improve the current measurement stuff. I will use the proper oversampling we already used for the voltage measurements, and I have some new parts which replace some old parts, that is wrong parts in our actual motor driver circuit. And finally we can add now the missing parts in our power supply. So we do all that small stuff in a single video, and that will be next week. Till then, bye.